Okay, so the next key lever is the fundamental theorem of calculus. And folks who came to mandatory tutorials on applications of integration, you actually already saw this problem. So you might want to just click pause and see if you can do this one by yourself, if you remember the theorem and how it operates in this question. For everybody else, here's what the fundamental theorem states. So it's up there on this page in very technical language, but what we always think about is new equals old plus change. That's what the fundamental theorem gets at. So in this problem, I'm recognizing that I have a continuous function on an interval, etc., with values of f and f prime given, and this known piece of information that the integral from 0 to 4 of f prime is equal to 8, that really triggers for me that I'm in a fundamental theorem question, because remember, change over here is really an integral. So the fact that I'm given that value of the integral really helps me to recognize what kind of question I'm in. And then I see this f of 4 here, and that is a new value that's being asked. Remember, the new quantity is always on top of the integral, so f of 4 is the new piece that I want to find out. So if I use new equals old plus change, that means f of 4 equals f of 0 plus the change from 0 to 4 of f prime. And when I start trying to solve this, I use my table for f of 0. That's not hard. I look at my table, f of 0 is 5. And when I look over here, the change that was given, that's 8. So my answer is 13. Okay, so key lever number 6 is the average value theorem. So if you have a continuous function, you can always find the average value by using this formula, 1 over b minus a equal to the integral from a to b of f. Another way of thinking about that is more aligned with what you believe an average is based on your mathematics in prior courses. An average is when you add everything up, and in calculus, an integral is an accumulator, it's an adder, and then you divide by however many things you have. So in this case, that division would be by the length of the integral b minus a. So those are equivalent statements, but you might like the second one better if you want to try and link this to your prior definition of an average. In our model problem then, we've got the level of air pollution defined by this function, and we want to find the average level of air pollution between 15 and 25 miles. So if I just use my formula, that's going to be an integral from 15 to 25 of L of x e to the negative 0.1x plus 1 over x squared dx all over 25 minus 15. And I'm going to just toggle over to a calculator and show you how I would do this. I'd make a little fraction for myself, put my integral up top. Whoops, let me try that again. From, what's going on? Shift plus, there we go. 15 to 25 of e to the negative 0.1x plus 1 over x squared. I'm going to insert another fraction here, 1 over x squared dx. And I want to divide, because it's an average, by 25 minus 15. What did I do, you guys? Oh, look at me. I don't want the integral from 15 to 15. No wonder I got 0. That upper bound is supposed to be a 25. That's more like it. 0.1437 is the answer to this average value question. So we can come back over here and record that in our notes. All right, and my last key lever is called the second fundamental theorem of calculus. I think in another video it showed up as a function defined by an integral. So you can see here when I dig into the new theorem, big F is the integral from a constant a up to a new function g of x of f of t, where a is a constant, f is continuous, and g has a derivative. The theorem states if you want to find the derivative of big F, that means you're differentiating this integral right here. A really cool result occurs every time where we just have to take f, the function inside the integral, evaluate that at g, and then multiply by g prime. Very similar to a chain rule, but a slight variation there. So when I look at our model problem, I'm asked to take the derivative of the integral from 2 to x squared of this function, square root of 1 plus t squared. That fits the mold perfectly. The derivative and the integral are right next to each other. We have a constant on the bottom, a function on top, and a function of t inside. So the theorem states take f, which is what's inside our integral, and evaluate f, not at t like we see, but instead evaluate f at the function on your integral g of x, which for us is x squared, and then multiply by the derivative of that function that we composed to get a 2x. That's all there is to it. Multiple choice will often ask you to simplify these, so if you want, here's what the simplified version would look like. We'll pull the 2x up front and write 1 plus x to the 4th inside, because x squared squared is x to the 4. But that's all we have here for our last key lever. So your next task is, of course, to come back to your packet. Beyond the key levers, you'll see your check for understanding is a free response today with a table of data. This is on 52, and we'll do those practice multiple choice questions together in class when I see you. So for now, try that check your understanding and use as many of those theorems as you can. I'll see you soon. Bye-bye.